Okay, today our topic is collector to base bias. So collector to base bias. So before going to that, let us briefly recapitulate what we discussed in the previous class. So previous class we talked about stabilization techniques and biasing techniques. In what do you mean by stabilization? What do you mean by biasing? So biasing circuits which provides stability of the operating point in case of variations in the transistor parameters like beta, IC0 and VB. So that is called biasing. So what do you mean by stabilization? So stabilization techniques refer to the use of biasing circuits which permits IB to vary so as to keep the IC value at a constant or relatively constant. So that is called stability factor. Okay, for getting the stability, we have to do some stabilization or biasing techniques or biasing methods. So in previous class, we discussed the first method. What is that? First method? Previous class, fixed bias method. So in fixed bias method, the stability factor is very poor. So that by using that fixed bias method, so at the output side, there is a instability. That means unfaithful amplification will occur. That's why we go for collector to base bias. So that is some small modification from fixed bias. It is a fixed bias circuit, but some small modification we will get the collector to base bias. Okay. So types of biasing circuits. First one is fixed bias or base resistor method. Second one is collector to base bias or biasing with the feedback resistor. Third one is voltage divider bias or potential divider. So these are the different types of biasing circuits. So today we will see the collector to base bias. Collector to base bias or biasing with feedback resistor. So which is derived from the fixed bias or base resistor method. Okay. So before studying the collector to base bias, we have to remember these points. First one is circuit diagram. So after that, you can analyze the circuit diagram. What is the input current? What is the input voltage? And what is the output current? And what is the output voltage? Okay. Then find the expression for the coordinates of operating point. Find the expression for coordinate of operating point. So operating point means VCE, comma, IC is called operating point. Then apply the KVL, Kirchhoff voltage law at the input side and find the input current. So use the input current and amplification factor to find the output voltage. So input current means here beta, base current. Use the base current IB and amplification factor beta and find the output current. What is the output current? IC is equal to beta IB. That is the meaning. Next, apply the KVL at the output side to find the output voltage. What is the output voltage? So output voltage is VCE. So we have to find the output voltage and output current. So that is called Q point. That is called Q point. Output current and output voltage, we call it as VCE, comma, IC coordinate. That is called Q point. So these points we will apply for modified circuit. See, this is the collector to base bias circuit. So you can recall the fixed bias circuit. So what is the main difference between fixed bias circuit and collector to base bias? The only difference is this resistance, instead of connecting here collector terminal, in fixed bias, this is connected at the VCC. So I will draw the fixed bias circuit. Okay. I will draw the fixed bias circuit. What is the fixed bias circuit? So transistor, this is ground, this one is the base. So this one is the collector resistance, and this one is the VCC. From this one is the VCC. From VCC to we are connecting the base resistance to base terminal. Now we are connecting collector here. Collector, just this is the change. In previous, from VCC to this RB is connected to base terminal from VCC. Here we are not connecting to VCC. We are not connecting to VCC. So base resistance is connecting from collector terminal to base. Okay. So that is the modification. It is a fixed bias, some small modification. This resistance, instead of connecting from VCC to base, we are connecting collector to base. That is the small modification. Okay. So this configuration employs a negative feedback to prevent thermal runaway and stabilize the operating point. In this form of biasing, the base resistor RF, so we are taken as RF, base resistor. So why we are taken RF means it is a feedback resistor. F for feedback. So we can also take RB also, no problem. RB, it is a base resistance or feedback resistance. Okay, is connected to the collector. So this is the collector terminal. Okay, instead of connecting to the DC source, see this line, this base resistor RF or RB is connected to the collector. So this resistance is connected to the collector instead of connecting to the DC source. Instead of connecting to the DC source, we are connecting this feedback resistor or base resistor to the collector terminal. Okay. So any thermal runaway will induce a voltage drop across the RC resistor that will throttle the transistor base current. So this is the concept, just modification from fixed bias. So what is the main difference? Instead of connecting the base resistance to the VCC or DC bias or DC source, we are connecting to the collector terminal. Okay. So same circuit I drawn like this. So this is the same circuit. It is a collector to base bias. So from the name, it suggests, we know that it is the emitter terminal. This is the base terminal. This is the collector terminal. So we are connecting a resistance, RB resistance, from collector to base. That's why it is a collector to base. Collector to base. This one is the collector to base. So this point is collector terminal. This point is collector terminal. So collector to base bias. That is the name. So you can clearly observe it is a 3-terminal transistor, emitter, base, collector. So the junction of base and emitter is we measured as VBE. So VB is the junction voltage. Okay, here taken output. So it is V0, V output. So what is the voltage exist from this point to ground? What is the voltage exist? VCE voltage. So it is a collector terminal means VC. This is the emitter terminal. So VCE voltage is exist from this point, from this point to ground in between. Okay, so we know that this one is input side, this one is output side. So we have to write the input KVL and output KVL. Okay, we have to write the input KVL and output KVL. So this one is the base resistance, this one is the collector resistance, this one is the DC source, collector DC source. Okay, so here current is both collector current and base current is flows through RC. Collector current and base current flows through the RC, then base divides. So base current is flowing through RB resistance and collector current is flowing through RC terminal. So this is the description of the circuit. Okay, first we have to identify the input current. What is the input current? IB. What is the input voltage? VB. So what is the output current? Output current is IC plus IB. What is the output voltage? VC. So this is the description of transistor, collector to base bias. Okay. So how to do this circuit analyzation from this? Okay. First, we have to write the input KVL. What do you mean by input KVL? We have to take the path like this. So from VCC to this RB, and this is the input side. See, this is the input side. Okay, from VCC to ground, this is the input side. We have to write the KVL. First, KVL VCC minus IC plus IB into RC, okay, minus RB IB minus VB is equal to 0 from this point to ground. This is the input side. Output side means this is the output side. So first we have to write the input KVL. So I will write here clearly what is the input KVL. Okay, so input KVL means VCC minus IC plus IB into RC minus IB RB minus VBE is equal to 0. So this is the input KVL. Okay, that means this is the voltage. So current into resistance, this is also voltage, this is also voltage, this is also voltage. So this is the KVL equation for the input side. So from this we have to write the VCC. So VCC is equal, what happened? This entire terms shift into right side. Okay, that means IB into, so we have to common IB. So IB is common. So here IB RC means here RC plus here IB common means RB. Okay, IB into RC plus RB. Here one term, other term is IC into RC plus IC into RC plus VBE. This is correct. See, just we have to write the VCC as it is. Then, so we entire term shift into right side means all are plus terminals. Minus is converted into plus. Okay, so this one is IC RC into IB RC. Here also IB RB. So from this and this we have to common the IB term. So here RB is left, here RC is left. So RC plus RB plus IC RC plus VBE is VBE. So this is for VCC. From this, what is IB? From this, what is IB? We have to write what is IB. IB is equal to VCC minus VBE. VCC minus VBE minus ICRC divided by RC plus RB. Correct? We have to analyze this equation, what I wrote. So VCC, this term is left side means VCC minus VBE, and this term also, plus term also comes to left hand side, minus ICRC divided by RC plus RB. So IB is equal to, this is the equation. But we know that what is IC? So IC is equal to beta IB. IC is equal to beta IB, we know that. Okay. So we have to multiply, that is equal to beta into this entire IB. What is the IB? So VCC minus VBE minus ICRC by RC plus RB, because IC is equal to beta IB. Beta is as it is. What is IB? IB is equal to, this is the equation. Okay, VCC minus VBE minus ICRC by RC plus RB. Okay, this is called collector current. This is called collector current. Okay, now consider the collector emitter. Collector emitter KVL. That means output side KVL. So this is the input side KVL. We wrote just now, that is the input side. We wrote just now, that is the input side KVL. Now I have to write the output side KVL. What is the output side KVL? VCC minus IC plus IB into RC minus, what is the voltage here? VCE voltage. So this terminal, collector terminal and emitter terminal, in between voltage is called as VCE terminal. Okay, I have to write this one. So VCC output KVL, VCC minus, what is the current? Collector current IC plus IB into, what is the resistance? RC. Then what is the voltage? Collector terminal to emitter terminal, VCE is equal to 0. This is the KVL for the output side. KVL for a output side. That means all terms will be voltages only. So resistance into current term is equal to voltage. This is equal to voltage. So this is the output KVL. So from this, what is VCC? So VCC is equal to what? How to write? VCC is equal to, we have to shift to right side, means all R comes positive. So VCC is equal to R. Otherwise, we have to take this one. VCE shift into right side means, so VCE is equal to VCC minus IC plus IB into RC. IC plus IB into RC. Okay. So this is for output equation. We have to calculate VCE. So finally we get IC and VCE. So this is the Q point. So we have already, we know that. So it is the battery voltage, collector current, base current, collector resistance. So we have to calculate VCE. We have to calculate VCE, and already we are calculating IC. IC is equal to beta IB. So this is called Q point. This is called Q point. Okay. So IC means what? IC is equal to beta IB. So what is IB? IB is equal to VCC minus VBE minus, this is the equation, VCC minus VBE minus ICRC by RC plus RB. Okay. Now we are already calculated VCE comma IC. Now we will find the stability factor. Okay, what is the stability factor equation? Stability factor. So I wrote, so stability factor S is equal to 1 plus beta divided by 1 minus beta into dou IB by dou IC. So this is the formula. Stability factor 1 plus beta by 1 minus beta into dou IB by dou IC. Already we know we are calculated dou IB by dou IC. That means what is IB? So this is the IB. I have to write this equation. IB is equal to VCC minus VBE minus ICRC by RC plus RB. I have to write. So I have to derive the IB. Okay, what is IB? So IB is equal to, already we calculated here. See, same thing I have to write. So IB is equal to VCC minus VBE minus ICRC by RC plus RB. So IB is equal to VCC minus VBE minus ICRC divided by RC plus RB. So this is IB. So now differentiate. So dou IB by dou IC with respect to IC. So we have to differentiate dou IB by dou IC with respect to IC. So that is equal to, so it is a constant, means it tends to 0 after differentiation. So this is constant, tends to 0, and only one term is there, minus. So with respect to RC means we have to get RC by RC plus RB. So this is dou IB by dou IC. We have to substitute this term. So dou IB by dou IC, we have to substitute here. So what we get? We have to substitute, means S is equal to 1 plus beta divided by 1 minus beta into dou IB by dou IC. What do you mean by dou IB by dou IC is equal to minus RC by RC plus RB. So minus, already it is a minus. Already it is a minus. So minus into minus plus. Okay. Then beta as it is. So dou IB by dou IC value is this one. So RC divided by RC plus RB. RC plus RB. So I wrote here same thing. So 1 plus beta by 1 minus beta into dou IB. So minus plus beta into RC divided by RC plus RB. So this is the stability factor, that is equal to S. Okay. So stability factor is 1 plus beta by 1 plus beta into RC by RB. That means this is S. If R is equal to very large, that means denominator term is large, so that total S factor will be small. So S is always, if nearer to 0 means more stable, nearer to 1 means it is unstable. Okay. For that reason we have to maintain the RB value is small and RC value is maximum. Then we have to maintain the then we have to maintain the this denominator is large. If denominator is large means S will be small, so that stability will be good compared to fixed bias method. Okay, so the stability factor, yes, this is the yes, stability factor, yes, is smaller than the value of obtained by the fixed bias only when we maintain the RC and RB value. We have to increase the RC value, we have to decrease the RB value, so that total S factor will be small. So that this is good compared to the fixed bias. So collector to base bias is compared to the fixed bias. So collector to base bias is very good stability. Okay. So these are the things already I derived. So what are the merits? So circuit stabilizes the operating point against variations in the temperature and beta. So replacement of transistor. So what are the demerits? So beta amplification factor is a fixed and generally unknown for a given transistor. So this relation can be satisfied either by keeping RC fairly large or making RF is very low. RF means here RB. So feedback resistance or base resistance. See, I will explain. So stability factor S is equal to 1 plus beta by 1 minus beta into RC by RC plus RB. So this is the stability factor equation. See here, by keeping the RC fairly large. So if RC value is large, here also large, so entire denominator term is large. If entire denominator term is large means S is equal to small. So total S is equal to small means so good stability. So here RF and RB are same. RF means feedback resistor, RB means base resistor, both are same. Okay. So based on selection of collector resistance, we have to get the good stability in collector to base bias. Okay. So let us summarize. So in this class, I talked about collector to base bias. So collector to base bias is from the modification of fixed bias circuit. So in fixed bias circuit, base resistance is directly connected to the VCC, whereas in collector to base bias, base resistor is directly connected to the collector terminal. Okay, that is the main difference. So this collector to base bias is derived from the fixed bias circuit. Okay, so after that we have to write the input KVL and output KVL. From this input KVL we have to find the IC. IC means collector current is equal to beta IB, and VCE. VCE means collector emitter voltage from the output KVL. Then stability factor is equal to 1 plus beta by 1 minus beta into dou IB by dou IC. We have to partial differentiate by IB. So in IB, VCC, VB are fixed only minus RC, RB by RC plus RB is the coefficient for RC resistance, so that we will get minus RC by RC plus RB. We have to substitute this IB, dou IB by dou IC in stability equation. We will get final equation 1 plus beta by 1 plus beta by 1 plus beta into RC by RC plus RB. So based on collector resistance and base resistance, we have to maintain the operating point, or we have to maintain the stability. If collector resistance is more, less collector resistance is more means stability is more, because stability factor it is nearer to zero. If uh, base resistance is very less, also stability factor is more. So we have to maintain these two values, collector resistance and base resistance. Okay, collector resistance should be large and base resistance should be less, so that we can get the good stability factor. So good stability factor means the circuit can be used as a good amplifier, faithful amplification we will get. Okay. Okay, thank you.